So the first method of calculating Fourier series is trigonometric Fourier series, and of course we're not doing any derivation over here. There's no point of doing derivation here, but this is the equation, the expression through which trigonometric Fourier series is expressed. Xt is any periodic signal. It is comprised of a naught, which is the average value of the periodic signal, and then a sum of all the harmonics and fundamental from n is equal to 1 to infinity. N, of course, is going to be the number of the sinusoidal component, which is part of xt. Again, n is equal to 1 means it's the fundamental component with the frequency of omega naught. Look at this n omega naught. Omega naught is the frequency, fundamental frequency, that is frequency of the signal xt. So n omega naught, n is 1, that means cosine omega naught t and sine omega naught t, those are the frequencies of the fundamental component. And as n will increase, n is equal to 2, 2 omega naught means it's the second harmonic, 3 omega naught means third harmonic, and so on and so forth. And then you have an and bn, which are the coefficients of the cosine component and the sine component of the Fourier series. So how do you calculate these values? Again, the formulas I'm giving you, I'm giving over here. Now this you should, all the engineers should remember how to calculate the average value of any periodic signal. This is pretty much standard. To calculate the average value of any periodic signal, you take the periodic signal over one cycle, you do the integration of that, that is you calculate the area of the periodic signal over one cycle and divide it by the time period. That's how you calculate the periodic value of any periodic signal, not just in Fourier series, but this is just a general formula. Anytime you have a periodic signal, and if you want to know what is the average value of that, you are going to basically calculating the area of that periodic signal over one cycle, and you are going to be dividing that area by the time period, and that's how you're going to calculate the average value of any periodic signal. So a naught is this. A, n and bn are given by these equations: 2 over t naught integral over one cycle, original signal, cosine n omega naught t dt, and n of course go from 1 to 3, that is fundamental, second harmonic, third harmonic, and likewise bn is given by this expression. So this is how we're going to calculate a naught, a n and bn, which once we calculate, we can substitute in the original periodic series expression, and then we will get the expression of that specific periodic function that you are evaluating, for which you are evaluating the Fourier series of. Okay, let's move on to the compact trigonometric Fourier series. So compact trigonometric Fourier series basically is based on equation 4.1, which is trigonometric series, but instead of dividing the sinusoidal waveform into two components, cosine and sine, basically we combine these two components into one, sine, cosine n omega naught t plus a phase angle, and then combine an and bn into a component cn. So if you look here, c naught is the same thing as the average value, so c naught is a naught as it is given over here, and cn is square root of an square plus bn square. Again, to calculate compact Fourier series, you will have to calculate, of course, the trigonometric Fourier series first, so that you know what is an and bn is, and you can calculate cn. But this is cn, and then the phase angle is tangent inverse of negative bn over an. So when you plot the Fourier component, you can plot, of course, c's versus n, right? You can plot c's versus n, or c's versus the frequency, and you can plot theta n versus n, or theta n versus frequency. So when if you're plotting c, the magnitude, that is c is the magnitude, when you're plotting c of n, then you have a naught, the first component here, or c naught, at n is equal to 0. So that's it, this is n, and I can go omega naught or f, n is equal to 0, or frequency is equal to 0, that's the DC component or average value. Then you have n is equal to 1, which is C1. Let's say this is C1, and C1 is at frequency omega naught, fundamental frequency, or f naught, whatever, right? So the frequency of this will be f naught if my scale is frequency in hertz instead of frequency radian per second. Then I have a component C2 at n is equal to 2. Likewise, if my x-axis is frequency, then C2 is going to be at 2f naught, fundamental the second harmonic, and so on and so forth. So I can plot all these components. So this is basically what? This is my spectrum. These are the values, the magnitude of the frequency components in the signal at DC, at f naught, at 2f naught, at 3f naught. So this is basically I'm plotting the magnitude of the spectrum here. And likewise, when I plot the phase versus the frequency scale or the n scale, then basically I'm plotting the phase spectrum. So I have a magnitude or amplitude spectrum, and I have the phase spectrum. So Fourier series, for all Fourier component, basically you have a magnitude spectrum and a phase spectrum. So that's the basis of how you are going from the time domain signal and looking at the frequency values, the component in the frequency domain or the spectrum. You move on from compact Fourier series to complex or exponential Fourier series again. So in this one, and this is the basis of discrete Fourier transform, so understand this one. We're going to use Euler's identity, and Euler's identity is simply e to the power jx is cosine x plus j sine x, and e to the power negative jx equals cosine x minus j sine x, right? So when you add these two together, e to the power jx plus e to the power negative jx, you're gonna get 2 cosine x. And if you subtract them, then you are going to get e to the power jx minus e to the power negative jx. You're gonna get j2 sine x. Okay. So if you want to know cosine function in terms of the exponential, then cosine function is e to the power jx plus e to the power negative jx divided by 2, which is right here. So remember, in the compact Fourier series, you have cosine n omega naught t plus theta n. So if you want to convert cosine n omega naught t theta n into exponential function, this you have the exponential Fourier series, then it will simply be using Euler's identity, e to the power j n omega naught t plus theta n plus e to the power negative j n omega naught t plus theta n divided by 2, using this right here. Got it? So we can write the compact Fourier series here. Again, this picture is not clear. I just copied and pasted from the communication systems book. So Cn cosine n omega naught t plus theta n is this. Of course, Cn is the coefficient, as we discussed in the compact Fourier series, coefficient of the sinusoidal components in Fourier series. And of course, since there is a 2 at the denominator, it's going to be Cn by 2, and the exponential components, these two components. And remember, this is why your cosine spectrum has 2 impulses. Again, go back to this is Cn. Go back to the spectrum that we discussed, cosine spectrum or x of f that we discussed, right? X of f has 1 impulse. When you convert the exponential signal into frequency domain, exponential signal produce an impulse. So you have 1 impulse at n omega naught t, or n omega naught, sorry, and the other impulse at negative n omega naught. So you have 1 impulse here, f naught, if I want to do f naught, so I have 1 impulse at the frequency of that. Let's say my frequency, if I'm plotting the third harmonic, so 3 f naught. So I have 1 impulse at negative 3 f naught, and then 1 impulse at 3 f naught. So that's where it came from, and this is the magnitude of the impulse, half of the sinusoidal component. So half of whatever the value of the peak value of the sinusoidal component, right? So this is where it came from. Again, I'm referring back to I forgot it was chapter 2 or chapter 1 where we discussed this. This is where it came from. Anyways, let's move on. So we multiply Cn over 2 by each of the exponential function, and then we basically distributed j n omega naught t plus j theta n. We distributed it into two exponential ej theta n, ej n omega naught t, and we did same over here. And we combined Cn over 2 e to the power j theta n, and here Cn over 2 e to the power negative j theta n. And we call this dn, this whole component, and we call this whole component d negative n. Okay. So dn is half e to the power j cn ej theta n, and d minus n half cn e to the power negative j theta n. Cn, remember, when you replace n by negative n, for Cn it does not matter. Remember, Cn is what? Is square root of an square plus bn square, right? So that's just a magnitude, so it does not matter negative n. But for the phase it does matter. If you replace theta n by negative theta n, then your phase is basically opposite of so positive, you get the positive value of theta and negative value of theta, basically, which shows that dn and d negative n, they are complex conjugate of each other, or d negative n is the complex conjugate of dn. That is, it has the odd symmetry in the phase, and it has even symmetry in the magnitude. So magnitude are same for n is equal to positive values and n is equal to negative values, but phases have 180 degrees phase difference. That is, one is positive and one is negative. Alright, so now we can write down the Fourier series in the exponential form as d naught, which is the same thing as c naught, which is the same thing as a naught, that is the average value, and then summation from 1 to infinity dn e to the power j n omega naught t plus d negative n e to the power negative j n omega naught t, right? So basically I'm writing down this equation right here in the form of dn. And to combine all these two terms, let's just combine first these two terms into one expression. We just start this, instead of n is equal to 1, we start this at n is equal to negative infinity, and we exclude 0 right now. So it says 0 is excluded right here. So n is equal to negative infinity to infinity dn e to the power j n omega naught t. So when you put negative values of n, that's going to become d negative n e to the power negative j n omega naught t, which is this. And when you put positive values, then it's going to be this, right? So one expression, just by changing the limits of the summation, is going to cover both parts of the expression. And you can also include d naught. Let's see right here. You can also include d naught. So here 0 was excluded, but if you don't exclude 0 and just write equation without saying 0 is excluded, then when n is equal to 0, what you're gonna get? You're gonna get d naught e to the power j 0 omega naught t, and e to the power anything power 0 is 1, so this whole thing is going to be 1, and you're gonna get just simply d naught. So the compact Fourier series can be even made more compact using exponential Fourier series through this expression. dn, of course, are the coefficients of the exponentials, and dn are calculated like we calculated a, n, and cn. dn is calculated through this expression. Okay, and this expression basically is the basis of our discrete Fourier series and discrete Fourier transform. So next we are going to discuss discrete Fourier series.